Optimize. A Journey Through Database Query Optimization. This course is filmed on location at Carnegie Mellon University in front of a live studio audience.
Alright, so today we're now talking about query plan transformation. So we have, again, the overall high-level view of how we build an optimizer. And so, I'll talk about this in a second. We're going to now go through the individual parts of the query optimizer, talk about how you actually want to implement them and optimize them, and optimize the optimizer and make things work efficiently. So before we get to all that, for you guys in the course, paper reviews will resume again this Wednesday on the 5th. You're reading a paper from on how to do the join enumeration in the hyper and umbra system. And then I know some people have submitted the PRs for the notes. Wayne and I will go through those this week and start getting credit for all those. And then project one will be due on Friday, the 28th. Again, if you haven't gotten started yet, please get started. Okay? Any questions about the reviews, the notes, or project one? Yes?
In the email that you sent us, the above average, below average actually mean anything, or is that just for
So everyone should have gotten an email from me yesterday from the an assessment of the reviews. It's just saying like, hey, maybe add more, like if you're below it. That's all it is. And yes, we do read them. We do. If people say, "Oh, Andy's not reading this," we'll find it. But anyway, so yeah. But in terms of getting specific feedback on hey, you got this completely wrong in the review, with so many papers and so many students, we're just not going to be able to do that, right? What's that?
How will that be graded?
Does it look like GPT? Yes or no? And did you do it? Yes or no?
What about the statistics for that?
No, I just told you. It's for your own guidance, right? Because people don't. Some people write too much, some people write too little, right? Sort of land in the middle. Again, this is an upper level graduate class, so it's really if you put the knowledge you're going to give out is the effort you put into it, right? Yes.
I was going to say, if we all start writing more, above average, the average
Sure. Yes. It's not scientific. It's just people in previous years I don't know whether I'm writing too much or too little. I'm like, okay, well here's what the stats are, right? It's not. There's no grading based on this. It's an upper level class, right? Again, the word special topics means something. It's kind of hey, we're here for a good time. Okay. I'll bleep that out. On that note, let me make sure I'm actually recording things. Yep. Okay. Cool. All right. So we posted. I mentioned at the beginning of the semester, and now we actually have the schedule all set up for the seminary series this semester. And again, this is optional. These are things if you want to go beyond the lecture materials in this course, and you just want more databases in your life, like I do. So again, the seminary series this semester is going to be a combination of people that have replacements for SQL or language that sit on top of SQL. So this is actually a rather new phenomenon where rather than saying SQL's stupid, let's get rid of it entirely, now people build their own DSL on top of SQL. You write your application or whatever queries you want in that, and then that gets transpiled into SQL that then runs on the database system. So convex and the Germans will talk about. I forget what the Germans transpile, but convex does. But Malloy, PRQL, OxQL, these a bunch of the DSLs later in the semester will do this. And then we also have the other sort of half of the seminar are the database people building query optimizers. Basically, the things we're talking about in this class, they're going to talk about how they actually implement theirs. And so Pino would be the first one of this. We have StarRock's guys are going to talk about the query optimizer. The inventor of MySQL and MariaDB, he's going to talk about their new query optimizer in MariaDB. That's later in the semester. So again, this is optional, but when you go beyond the things we talk about in the course, I encourage you to check these things out. And the great thing about the ones where they're going to talk about how their query optimizer is actually implemented is now you'll pick up on things. Oh yeah, we're doing bottoms up or tops down. This is how we're doing this transformation, or we don't do this kind of enumeration. Now all the things that we've been talking about this semester start to click and put in the context of a real system, and you realize I'm not making everything up, right? Okay, again, we'll post this the schedule and everything on the on Piazza. All right, so where we're at so far in the course, well, in the last class, we spent a whole day talking about cascades, right? And cascades was the successor to Volcano from the Graphy guy. And it's basically Volcano with the key difference that you don't have the separate generation and cost analysis phase. Everything, all these transformation rules are thrown into the mix, into a single search space. And the optimizer is then free to decide in what order it wants to apply rules, whether going transformation first or physical first, or sorry, logical or logical to physical first, based on what it knows about what the query wants to do, and additional guidance or promise mechanisms that we can add to our implementation, just again to sort of push or nudge the query optimizer in the right direction. Another key thing is that they have this task-based transformation concept where like there's all these tasks that can apply rules and do different things, and you're throwing them, at least in their implementation, to a stack, and you're picking things off of the stack rather than just sort of recursively calling thing after thing after thing, right, and doing a depth first search. Then the way they're going to avoid the explosion of just recomputing the same thing over and over again is through this memo table. Volcano sort of had the similar thing, but the one in Cascades was more formalized and more rigorous. So as I was just saying in the beginning, like where we're at now in the semester is that we spent time talking about System R's optimizer and Starburst and Volcano and Cascades, and those are basically going to be the high-level architectures of or blueprints, if you will, of how to build a query optimizer. Not throwing Postgres in there because that thing's a rat's nest, right? It's just house on straws, but on top of house on straws, like it's sort of. No one sat down and thought through, here's what the Postgres optimizer is going to be for the longevity of the project, as far as I know. So I don't want to include that. But the Starburst one and the Cascades one, that's where people who have built multiple optimizers really sat down and said, okay, here's what this thing actually needs to look like. Here's how to actually architect it so that we can not only be extensible and add new capabilities to support things beyond maybe the relational model, but just maintaining and engineering and the thing over long periods of time. And making it easier for the system developers to add new optimizations. All right, so that's the big thing we're at this point. We know that, okay, we know how to build something that looks like Starburst. We know how to build something that looks like Cascades. So now the quality of the plan that's going to get generated by these optimizers is going to vary on a lot of factors, but the three key facets that we're going to care about for the next few weeks is what the search algorithm is going to be. It's actually how we're going to do the enumeration of the alternative query plans we could have to decide, can we find a better one? Right? And that's the top-down versus bottom-up kind of thing. Then there's also the cost model to say how can we predict whether one query plan or one alternative is going to be better than another based on statistics and other things that we're collecting either through an analyze phase or through hints provided by somebody else. Like, it doesn't matter. Well, it does matter, but we'll see how to handle that. But certainly, like if we have a crappy cost model, who cares about everything else? Because if our statistics are way off, then we're going to end up picking bad things. And then the last one is going to be the transformations. And this is what we're going to talk about today. And starting on Wednesday this week, we'll then pick up going back to the top again, the search algorithm. But the transformations are going to be the piece where, again, if we don't have the ability to recognize that, hey, here's a better alternative plan for this query that we're looking at, then again, who cares about how good our search algorithm is or cost model is? So you need all three of these things to be good. So that's why we're going to go sort of through each of them one by one. Right? And then it's all about the combination of accuracy, as I just said. Like I want things to be correct when I think one query plan is better than another. And then it's also going to be an efficiency. And we'll talk a little bit about today, and we'll see this definitely next class on Wednesday. Like if my search algorithm is like super, super slow, then it doesn't matter how great my cost model is or how great my estimates are or my transformations are, because I'll never even get to even explore everything. Likewise, if it takes me forever to generate all the transformations, then I may never get to exercise the other ones. Again, so it's symbiotic between these different factors, but it's a combination of efficiency and accuracy that we're going to care about. All right, so we've already defined what a transformation is through multiple times, but just to put it now on a single slide, and then that'll guide us going forward. Right, it's the idea that we want to have some kind of mechanism in our query optimizer that's going to allow us to change our query plan that we're currently operating on, we're trying to optimize, into a different form, a different structure different shape, if you will, where the new shape they're going to end up with will be semantically equivalent or logically consistent with or correct in regard to the original query plan that we were dealing with, right? And in some cases, sometimes a transformation rule, if a transformation rule might put a query plan into an invalid state where the result would not be correct, then, and we know we have to apply another rule immediately afterwards to make sure that is correct, then we essentially want to combine them together in what the Cascade paper or Cascade chapter talk about being like a macro rule, right? So when you apply one transformation, you always want to end up on the other side with a correct query plan, because you may, the search process may truncate right there. You may not even get to, again, make any corrections. So the way this is going to work is that we need to, we're going to rely on our knowledge, domain knowledge of both the system we're building, as well as the relational algebra equivalencies that we know about, and combine that with information about what we know is in the database in terms of what the schema is, like what constraints there are, what the foreign key dependencies, references between different tables, the data types and so forth. And then also what the data itself looks like in terms of selectivity, or the number of tuples, the size of the tuples, and so forth. So it's really a combination of these things that we're gonna use to guide our decision making to decide whether we want to apply a transformation rule or not. So our goal is going to be during this entire process is, of course, we want to ideally end up with a lower query execution cost. But another key factor also too is that there may be some transformations that we want to do that may actually make the execution costs worse, at least immediately. But because we do this transformation, that unlocks a bunch of other transformations that we can now do to then end up with a query plan with a lower cost. There's one key example in the chapter you guys read. I mean, you don't have picked up on it, like for this last one here. Remember what it was? Converting outer joins to inner joins, right? We'll see that in a second. Like that one is a huge one. If you can do that, then because outer joins always can't be flipped around. So it's things like that we want to do to make the optimizer essentially be more efficient or uncover the optimal query plan or the near optimal query plan more quickly. All right, before we get into the transformation we want to talk about today, I always want to note that sometimes in other lectures and other classes, or in like an intro class, or if you're taking 721, we oftentimes show the expression trees of like predicates as this like separate thing that's either embedded inside an operator, right? Or like, for example, if you have a join operator, an internal attribute of the join operator itself would be what's the join predicate. But in the book, although they're not always consistent, they're going to represent predicate expressions as just another logical operators in the query plan. So I'm going to try to follow along with the same sort of nomenclature or representation style that they're going to use, right? So if I have a query here, select from a table S, where S.A is greater than 10 and S.B is equal to 20. So they'll have this filter operator here. And so normally sometimes in other lectures, I would show the expression tree as being internal to this filter operator, right? And instead what they're going to do is say it's actually like a child operator, right? Again, I bring that up, just want to be consistent with what they're doing. That way, if you follow along the book, what I'll say today will match with them. Again, they're not always consistent. Sometimes they, instead of filter, they put select, right? But I just try to normalize everything, make it more clear. And then the pseudocode, I know they put the join clause in as an operator, as an attribute to the join operator. We can ignore that. All right, so today we're going to talk about sort of the four main categories of transformations we're going to do. So access paths, inner and outer joins, and then group by. And then I want to finish off talking like sort of one example of like special case scenarios you could have in your transformation rules, where if you recognize immediately that the query plan is following the combination of the query plan and the schema that the query is, or on the data the query is trying to access, if they follow a known design pattern, like a star query or a snowflake schema, or snowflake schema and a star schema, then like there's rules you can say, okay, immediately put this in the form I know that's going to be almost near optimal choice. We'll see that at the end. All right, so the first thing we got to do is figure out how we're actually going to even access tables, relations in our table, or in our database. So the goal here is, again, we want to choose the access methods that will access the data that we need. You can think of like base relations, leaves of the query plan, and that's going to have the lowest cost for us. So again, we're not talking about how we do cost model estimation as yet. That'll be in a few weeks. But obviously, again, given your background knowledge of taking the intro database class, we know that the things that are going to matter to us are going to be some combination of like how selected the predicate is, what the predicate is even based on, what columns in the table there's even accessing. Is the table or the index they're accessing sorted, and I'm going to need that sort order somewhere else in the query plan. If there's additional things that maybe were added to the table or the index, like zone maps or include clauses. And I realize that I don't teach in the intro class what include clauses are, but I'll do one slide on that real quickly. Other things like encoding scheme or the compression scheme of the data itself, right? And if we know that our predicate can operate directly on compressed data, right, without having to decompress it, maybe that's something we want to choose that path versus another. So again, the idea here is we want to figure out for a given table or given relation in our table, how should we access it? Should we go through an index or should we basically view a sequential scan? All right, so let me quickly talk about the include columns just because I think they're cool, and we didn't get a chance to talk about them in the intro class. They're cool and not widely used, even though it can make a big difference. So the basic idea of an include column in an index is that it allows you to embed additional columns in the index that aren't actually going to be part of the search key. So here I can define an index on some table foo, and the key that I'm going to do lookups on is going to be columns A and B. But then I have this include clause where I'm going to add C, and that just means that in the leaf nodes, assuming this is a B plus tree, in the leaf nodes will be the actual value of column C for every single tuple that's being indexed or being referenced in the index. So all the inner nodes, the guideposts that get you down into the leaf nodes, that'll just be on indexes or columns A and B. And then when I land on a leaf node, when I say, okay, well, what's the record ID or the row ID I need to follow from this leaf node to go get the original tuple, along with that, the record ID and that payload will be column C. So now for certain queries, I can essentially execute them as a covering index query, meaning I don't actually even have to go look at the original tuple, right, assuming it's a row store, because everything I need is in the index. If it's being packed in as an include column, right? So in this case here, select B from foo, where A equals 1, 2, 3, and C equals Wu-Tang. So for A, since I have that as the prefix, my B plus tree for index foo, I can do a lookup on the index on A, then traverse down, get to the leaf nodes with the starting point of A, and then find all the A-B combinations where A equals 1, 2, 3. I can't do anything with the C on my index probe down to the leaf nodes, but when I land in the leaf nodes, and now I start scanning along on all the values, all the index keys where A equals 1, 2, 3, I'd go peek and look and see, hey, does that C value, does that equal Wu-Tang? If yes, include it. If no, exclude it. And what's even better also too, in this case here, because I'm also packing in B as the key, so even though it's not being referenced in the where clause, I still can get the value of B because it's part of the key. So in this case here, assuming it's a row store system, for this query here and this index on this table, I never have to go look up the actual tuple itself. I can answer this query just through the index. Okay? Postgres added this, I think, a long time ago, but it's in Postgres 11. So what is that? Maybe 8 years or so. But like SQL Server, Oracle, and all these guys had this for a while. All right, I'm bringing this up because we want to mention this as we start talking about the access methods for in the one example here. All right, so this parlance here, again, this taxonomy of here's the different access methods you could have. This is going to be SQL Server specific, but this is generic enough where I think it's still applicable to a lot of systems. So the default choice, no matter what, to access a table is always going to be the sequential scan or what they call a table scan. Right? If I have no indexes, I have a way to iterate over the pages in the heap file for the table and still access everything, right? And for some systems, this is okay. Like this is like for the column store, this actually might be the fastest thing to do. Like in Snowflake, you can't do index probes. You can only do table scans. at least for the non-hybrid tables. We can ignore that. But then for indexes, there's three ways I could actually do lookups on them. The first is do an index seek, where I'm going to retrieve all the tuples based on some predicate. If it's a thing of like a range scan, I could get all the things I get all the tuples for a single predicate for like an exact match on a key. A subset of that would be, or a special case of the index seek would be called what they call an index key lookup. And this is where I do a probe in the index, and rather than getting actually the tuple, I'm just getting true or false about whether the tuple actually exists or not. And this can be useful for some of the transformations that they're going to want to do, because I don't actually want to get the tuple. I just want to see whether it exists. And I don't have to worry about copying all the data around. Index scan would be, again, a range scan on the index. So the idea is that for a given index, we would look at the catalog. For a given query, we would look at the catalog and say, well, what predicates is this query accessing? Sorry, what table is this query accessing? What are the predicates on that table? And what indexes do I have available to me? And that enables a bunch of these transformations that I can decide now which one's going to be the best choice for my query. So if I want to try to pick a single access method for a table, then again, it's just as I said, I look at all the choices that I have available to me, and then I'm going to pick the ones that will be I think it's going to have do the least amount of work. And so this picking what indexes avails me is sort of a qualification round. It's like deciding of the index choices that I have for this table, which ones can I use for my given query? So if I have a bunch of indexes on a bunch of tables that have, on a table that has a bunch of attributes, and I don't reference any of those attributes in my query, then I don't need to consider exploring it, right? Because it's just going to be a sequential scan from along leaf nodes, and that's typically going to be a bad choice. In other cases, again, I don't think I taught partial indexes in the intro class, but in some cases you can have where clauses in indexes. So you can say, create an index on table foo where date equals February 2025. And then you make another index where date equals January 2025. And then now my where clause, if I've referenced that date field or date attribute, the optimizer can pick which of the partial indexes are going to be the ones I should use. So again, this qualification round. It's not just like, am I accessing the attributes? There may be additional properties on the indexes that could determine whether I can access things. Another obvious one would be if I'm doing an equality predicate, then I can do a lookup on a hash index. But if I have a less than or greater than, I can't do a lookup on the hash index. And so it would disqualify that. And as I said, if there's no good options, then you always just fall back to sequential scan, table scan. All right, so look at a simple example here. This is that query we had before. Select A and B from S, where S.A is greater than 10, S.B is equals to 20. So if we look at our two indexes that we have here, right? So we have a index on A with the include columns C and B, and index on B with include columns C and A, right? So again, fallback option is to say, okay, well, I don't want to look at any of the indexes. I'll just choose the sequential scan physical operator for this, right? And again, think of like, again, I'm not showing this in Cascades, but like there would be a memo table, or say there would be a group where I keep track of, here's all the alternatives I would have for the expression get table S. And so one of the things I would put in there as an expression that I may want to explore, a physical expression I may want to explore, will be the table scan option. But let's say I want to try to do an index scan on this, right? So I could look at the first predicate here, whereas S.A is greater than 10. Well, I have an index on S.A. Again, assuming it's a B plus tree, so we can do a range scan. And so I could create a transformation that would convert the get operator here into an index seek, right? Because that's doing a range scan on the index. And then now I'm going to move the expression that was in here under this logical AND operator. That gets extracted out and is now being part of the index seek. So now I'm referencing what index I want to scan, and then here's the predicate I'm going to apply to determine what my starting point is. And then in some cases, you would have a termination point as well, like the upper bound of when the range scans to stop. All right, so that's an example. Obviously, like again, we would say S.A, we have a range scan, pick the index seek physical operator. In this case here, now we have an equality predicate on S.B. So again, we could use this index on B itself, and then do another transformation that would convert this into an index scan, because now we're going to be retrieving exactly one key. Sorry, for a single key, give me all the attributes or the matches in my index. And again, same thing. We just move the s.b to be attached to the index seek or index scan operator, right? And again, the cost model will then determine which of these are the best approaches. But we're not there yet. Yes. The seek would be like it could be unbounded for how many things I may like for across multiple keys I may be looking at, right? So I'm saying where s.a is greater than 10.
So seek is for like a range of values of this key.
Yes, but in the actual implementation itself, it's just another iterator, assuming that say this is not a unique index. So it's basically give me all the key value pairs where s.b equals 20. And it's basically you're calling get next on the iterator over and over again. It's equivalent to this. It's just this is sort of unbounded. You could keep going forever. Until you reach the end of the tree. Yeah. It might be, again, this is what I think this might be a distinction in SQL Server, but as far as I know in Postgres, there's not a distinction between the two. All right, there may be other cases where we want to actually where no one access method is the best, and therefore we could choose multiple access methods. And now what ends up happening is that it seems like it'd be wasteful to have to access two indexes, but it turns out doing that allows us to reduce the overall amount of work we have to do, because now we may not have to do a bunch of sequential scans or a bunch of lookups in the table itself to go find the additional attributes we need to determine whether they're going to satisfy our predicates, right? So going back here, I'm not showing the full physical plan here, but like I'm doing index scan when s.b equals 20, but then I still got to go figure out whether they're going to match s.a is greater than 10. So what would happen is the physical plan would get converted to actually some kind of lookup on the table, all right? Because you would get back the either the row IDs or do the lookup on the row ID to go get the table from the table itself. So you're going to look up against the table heap to go get the rest of the tuples you need, and that could be really expensive, right? Because maybe this doesn't satisfy a lot, or this other one doesn't satisfy a lot. But the combination of the two of them is quite selective. But since I got to go to the table to get the other attribute, and that's going to be slow. So in most systems, actually, I don't know whether SQLite can do this, but I know all the commercial systems can do this. Postgres can do this. MySQL can do it. Although people say the MySQL one's slow because the implementation is poor, but that's what the documentation says, or that's what the blogs say. But the basic idea here is that we want to select two or more indexes to actually access based on our predicates, and then we're going to take the intersection or the union, depending on what the predicate is, whether conjunction or disjunction. Take the intersection and combine the results of the two index lookups, and then that combination would then produce the correct answer that we're looking for. So in the book, the way they're going to represent accessing having multiple access methods on a single table is that they're going to represent this as a logical self join on the relation you're trying to access, and it makes sense, right? You would say I'm going to do some scan on one side of the join for the same table, get back the results based on whatever access method I want to use. Now I'm going to take the output of that and join it with another access method on that same table, and then putting that together will produce the result that I'm looking for. And whether or not SQL Server actually implements this as just regular joins, I don't know. But I know in case of Postgres, they will. I don't think they even get to representing a self join. They just recognize that I could have multiple. I could do multiple index probes on the table, and those combine them to a single physical operator called a bitmap heap scan, bitmap index scan or bitmap heap scan. But it's conceptually it's basically the same idea. So going back to our example here, so say now we get rid of those include clause indexes, and now we just have just an index on A by itself, right? So we could choose this and say that yep, that looks good, and for that one index here, what we'll do is we will have one side of this nested loop join. We're going to do a index scan on it, so that's going to be a range scan to do a lookup to get all the keys, all the tuples where s.a is greater than 10. But then we now need since this is not going to actually give us the actual value of B that we need for this query, we're going to do another probe into the primary key index. Again, and they're assuming that this is being organized as a clustered index or index organized table. So like the leaf nodes of the primary key is actually going to be the tuples themselves. So this probe just gives you the row IDs, and then given that row ID, you would then do a probe into the primary key to then get the actual tuple that you would want, right? And then that gets filtered up here to produce the final result that you're looking for, right? So they're choosing this index to do the index scan, but it's only kind of giving you half the data you need, just telling you whether it's finding the records that satisfy this predicate. To get the actual data you need, you have to go down the other side here. But again, in the intro class, we talk about doing tuned index probes and ORing them or ANDing them together, taking the intersection, and then that would produce all the record IDs would match as well. So this is conceptually the same idea, but the idea is that the nested loop is actually, this is going to give us all the data we need. This is just a match that we're passing along down here to say, find the actual tuple that got matched down here. So when is this a good idea? Well, it depends on a lot of things, right? It depends on what the data structure you're using to represent your data, right? I just said like this would only really make sense if you're doing this, if this is a clustered index or index organized table where the primary key lookup will give you the value that you need for B. In other systems like Postgres, for example, I'm not saying this is a bad thing about Postgres, I'm saying this is the way Postgres is implemented. This doesn't make any sense because if I do a key lookup on the primary key, all I'm going to get back is the record ID, and I had that before over here. That doesn't help me, right? So I was better off maybe if I had an index on B, do an index on probe on that, then take the intersection of the two of them, right? Obviously, it also depends on the selectivity of what the predicates are. Like if this is going to match 99% of the tuples, then I'm just wasting work here because I would have been better off just sequential scanning the table and finding all the tuples that would match this, on my own based on that. There's other things about the multiple access methods that we don't get into, like the actual implementation. Like in Postgres, for example, they'll try to use they maintain a bitmap to say, here's all the, my table has a million tuples, so I'll make a bitmap of like, say like, I don't know, a million bits that I just set a bit to true. I know if I matched it when I'm sort of on one side of an access method here. But if it's larger than a million, then they'll switch to like a Bloom filter. So you may have false positives in your matching, and so they have an extra step to actually go look at the tuple again and see where you have a match. But again, from an optimizer perspective, that's just included in the cost of whether an access method makes sense or not, which is the combination of the selectivity of the predicate or the size of the data. Okay, so now that we know how to pick the access methods for our base relations, we now need to do what the most common thing people do in databases, other than select star queries or select count star, and actually start joining things together. And so, as we said before, the goal here is to generate all the possible different join orderings we have for the query. So not all possible, but the ones we think they're actually going to be beneficial for us. And we're going to special case, or not special. We're going to start off talking about inner joins or inner echo joins because they're the most common. But we still need to handle all the corner cases and be aware of, as we're generating the join orderings, especially when there's outer joins, could we violate the correctness of the query plan if we start swapping things that shouldn't be swapped. So the challenge is going to be, especially in a transformation-based query optimizer like Cascades, and we'll see the German's approach that doesn't have this problem next class, is that although the memo table is going to make sure that we don't waste time exploring duplicate expressions or portions of the subplans in a query over and over again, because we just look at the memo table, yes, we've seen it before, don't actually explore down that branch. But the cost of generating these transformations can be quite expensive. And again, Cascades got around this problem because they wouldn't eagerly transform everything all at once. Prior to that in Volcano, they did, and that blew up the search base. So the problem is if you just do an exhaustive transformation of all your logical rules of changing all the possible join orderings you would have, the space complexity of all the transformation or all different alternatives you have to store is 3 to the n. But the computational complexity of actually applying all of them is 4 to the n. because you just keep recursively doing the same thing over and over again, right? It's basically saying the cost of not only is the cost of exploring the different combinations you have expensive, the cost of actually generating all the different combinations you have is expensive and wasteful as well. And so there's this paper from some of the 90s where they show, for a small number of relations, how many different operators you'd have to consider in sort of the member structure as you expand things out in other transformations, and how many of them are just all being duplicated, right? And as you see, it's not growing linearly. All right, so the way we're going to get around this in a transformation based query optimizer is we're going to leverage information about the behavior of the transformation rules to decide in the order in which those transformation rules can get applied. And then when we apply a rule, it would then disqualify on a per operator basis what additional rules that we could then apply again in the future. And the goal here is that we want to, again, not end up generating duplicate expressions or even looking at, even considering should we even apply this rule, like checking the pattern in the query plan itself to go see whether a rule should apply. We want to avoid that check entirely. And so the way we're going to do this is that on each operator, we're going to maintain a small bitmap that keeps track of here's the transformation rules that I have applied, and which ones am I allowed to apply. And so the idea is if a bit set, basically it's disabling that you're allowed to apply this transformation rule on a per operator basis. How they handle combination of multiple operators, that's more complicated. You basically have, I think, sort of virtual operators, virtual rules represent for given one operator. Here's the combination of rules that can apply. But the paper doesn't say that. This early one is based on, I think, Volcano, not Cascades, and so it's more simplistic. But this is one of the things that, again, the textbook, the book doesn't say. That's my understanding how they do it. All right, so here's sort of 4 basic rules when you do join enumeration. That, again, a lot of things we've covered in before, how to do commutativity, right associativity, and left associativity. Exchange is to be able to, it's like commutativity, but you're just sort of swapping one element of a subplan for a join with another element on the other side. In this case here, I'm joining W and X and Y and Z. So I'm going to swap the X and the Y. So W is still on this side, Z is still that side, and I'm just swapping the position of Y and X. All right, and the idea here is that when you apply a rule, you would then specify for some operator in the output of that transformation of what rules are not allowed to be applied in the future again. So in the most obvious one here, like if I do the commutativity one at the top, like X goes to Y, and X join Y becomes Y join X, then the new operator that I'm spitting out is this join 1. Well, I don't want to go ahead and apply, obviously, the commutativity rule again, because that's going to just put me back where I was before, right? We're looking at a more complicated example here, the right associativity. So if I apply this rule and then I end up with this new join 2 here, then I don't want to apply R2, R3, and R4 for this join operator here, right? But I am allowed to do the commutativity rule because now I may want to put the join of YZ on the other, on the outer side of the join, so I can swap the order. But then, of course, now once I do that, then that blocks doing any other operations again, which again, you sort of see the circular dependency, because if I do that commutativity order, commutativity swap, put me into rule 1, if I then apply the right associativity rule or the left associativity rule, I'm going to be basically swapping back and then stuck in an infinite loop. So I'm just going to set a little bit and say, okay, if I go apply a rule for this given operator, if I generate it from this rule, then here's the rules that I cannot apply. And again, it's only for the subset of the operators that got generated here. So look, I created a join 3 here, but now I'm free to do whatever I want inside of that thing, right? And that won't put me in an infinite loop. So I can go ahead and swap the order of Y join Z become Z join Y, and that's fine. And again, depending on the query, that may be what I want to do. So by again just keeping track of like when I apply a rule, what rule, understanding sort of the categories, the classes of these rules, and what they're actually doing, and you're sort of linking them together and say, if I do this, then I can't do this other one here. Is that clear? Yes.
For rule 4, why can't we apply rule 1?
This question is for rule 4. Why can't you apply rule 1? Again, it's just for this, right? So you could change the join 3 and join 5. If you do say the commutativity one,
So then you wouldn't be able to switch it back because 1 disables 4 and you would be good.
yeah, let me think about this. So it's I think because it's like so heavyweight that's why you don't do that. Like in terms of like just moving a whole subplan from one side to the other side. I don't think it limits you in any way. Let me think.
I mean, wouldn't it all be abstracted in groups and expressions, if at least we're using cascades? So it being heavy would not be a problem.
Yeah, you're right. Yes. So his statement is, and he's correct, that like it's all abstracted away as groups and cascades, which this paper is again based on Volcano, but like this is just WX. I'm not saying what the hell I'm actually doing, how to get it. So it's not a really heavyweight operation. It's just moving the group to one side or the other. Actually, yes, I don't know the answer to that one of why exchange is a special case and it blocks everything. I think, yeah, now I remember. Okay, so the order in which they get applied is the top to the down. So you would do commutativity first. So you could swap these, right? And that's fine. And then it may be the case that you sort of iterated over this and swapping things around, and then you get to this last one, and at that point you would have already explored the commutativity swap on this. So you don't explore it.
Swap it to begin with, and then you block 4, then 4 will never check.
Wait, say it again. If you swap it,
Say you had this from 4 join 1, and it applied at some point earlier. You applied rule 1.
yes,
Which if you applied 4 would give you the inverse of what you did of 4 down here, but you won't ever apply rule 4 because rule 1, once you apply it, you aren't going to do 4 on the new one. Does that make sense?
Yeah, I understand. Yeah. Let me double check that because R4 is definitely useful, right? Because I want to be able to move things around.
Right. I just would want to be able to do like for the right where 5 and 3 are swapped and see if that's better than the other one. I don't see how we get there. That makes sense.
Yeah, I understand. Yeah. Let me double check what gets disabled, and I'll post some Piazza. Again, I think that you end up through the first 3, you would end up with you may have already explored this, and this is sort of a catch-all at the end. But I'll double check. Yes.
Now I have a general question about having any of these disabling mechanisms in place. If you're using cascades, you have a memo table, and in there the expression will already exist. And so it will probably have a marker saying that, hey, I'm either A, exploring this, or here's the cost of that expression. So disabling them really just avoids one function call, does it not?
Yes.
So that's useless. Well, it's pennies on the dollar, right? Like it's not that much.
So his statement is, and so he's right. Going back here, it's what I'm saying is like this is like with the memo table, you avoid doing the exploration of something you've seen before. Exactly. And so what I'm showing here is just the ability to not check.
Yes.
So as you said, it's one function call.
Yes.
But again, if you're exploring, thousands or tens of thousands of different,
Because this big set is right next to the item, but in order to look up the memo table, you have to jump to the hash map, which can be quite costly.
So you're both right. So what they're trying to avoid is that jump to the hash table. You say, oh, well, that's 01, who cares, right? And he's correct that like it's jumping to some other data structure, doing a luck on, right? Yes, it's constant time, but like if you're doing this tens of thousands, millions of times per query, not doing that extra jump and then evaluating whether something could match or not, like that's a big win, right? And again, this paper is written from '97. Computers are crappier, like slower. So like in their world, this is just as problematic. And because also we didn't really talk about this, but like the complexity of the queries now certainly have gotten more complex than what they were in the '90s, because the SQL has expanded, the people have more data, right? Different tools are generating, different dashboards and things like that. But the curve of the complexity, right? Where like most of the queries aren't going to be complex. So they were trying to deal with two table joins. Most queries look like that. Like if they're new joins, it's going to be 2 table joins. We're in the same world. So, they're trying to basically plan the same queries most of the time that we're trying to plan today. So yes, like in that environment, avoiding that lookup to see should I even apply this rule may have a bigger effect on performance than what it would today. But it's still going to be used for us again when you start exploding out the number of tables you want to join. All right, so I'll follow up with him and like let me double check like you go from top to bottom. Let me check how you can still end up with this if you're disabling the like R1 for example on that join 4. Okay, all right. So then this sort of next most obvious optimization everyone does is predicate push down or also predicate push up. And so the idea here is that if we recognize that a predicate does not reference any attribute that's going to be in that requires the output of the join, then we want to push down the predicate to be below the join so that we're filtering things up before we get into the join, right? So in this case here, say that this wants to look on s.a where it goes 1, 2, 3. So in that case here, that's a cheap computation, so we definitely want to push that down below this join here. But it could be also the case too that even though if the attribute still only references things that don't require the full join, but the computation itself is expensive, right? The join's another filter, basically another filter too, right? Because it's trying to match things on the outer and the inner. So it may be the case that the predicate itself is computation expensive to execute, and therefore I want to keep that above the join. Right? And this is why again when the query shows up, we parse it, it runs through the binder. The binder is trying to figure out what all the columns you're trying to reference, and then it's going to try to split up whether the optimizer does or the binder does, it's going to split up all your predicates based on the conjunction so that they're sort of separate units, because then now you can start moving them around, in some cases even duplicating them if you wanted to. You can start moving them around independently in the query plan based on where the best place today is to actually execute it. So in this case here, even though this could be below the join, the query optimizers say, well, I know computing the like is computation expensive, so therefore I don't want to put it above the join. And then now in my rewritten query, I only move P1 to be a filter below the join, but I'm keeping all the elements on the other side. Right? Yes.
Won't be like an advantage when you have like an OR operation, and it will make sense to have like push down and then because you can filter out a lot of things.
His question, your statement is, this only works when you have conjunctions where I know I can push things down and I don't have to check something else. Yeah. Not for everything, right? Because you could have, like again, if this was like s.id equals 123 or s.b equals 456, right? That could be pushed down. That's fine. Right? It's when things reference maybe from the 2 tables on the join together, right? s.id plus 1 equals t dot value plus 4. I need both of them, so therefore I have to do it after the join. But disjunctions you can still push down. All right, so the last one is again how to transform what join operator you actually want to implement. And again, this is going to depend on what the predicates are and what the data actually looks like in terms of what's coming into the join. All right, we already mentioned this. Like most obvious thing would be like a hash join. If my join clause has like a less than or greater than on the join key, then I can't use a hash join because I can only do equality predicate lookups. They're not that common, but sometimes you see joins that look like that. Anti-joins would be another one, like where something doesn't equal something. That's very common in like data cleaning workloads. You're trying to think like, have I seen this thing before? Yes or no. right? So in that case, you can't use the hash join. Merge joins, or cert merge joins, like the data coming into it obviously has to be sorted on the join key. And we talked about how to use enforcer rules to make sure that the data does look like that. But if it doesn't, then the optimizer needs to know I can't pick the merge join operator. And like the sequential scan or table scan is the fallback option if we have no other choice, for our access method, the nested loop join, for as slow as it is the fallback choice for when we want to join data together. Because no matter what the predicate is, no matter what the data looks like, the nested loop join will produce the correct result. It'll be slow, but it'll do it, right? So another thing that that happens too during the query optimization that the book doesn't talk about is, for these join operators, there's sometimes additional parameters that specify how the thing will actually run at runtime, or run when you actually execute the query. So the most obvious thing would be if I'm doing a hash join, I want to be able to know what size the hash table should be when I run it, right? And if I'm doing like in a row-oriented system like Postgres, or if I'm using like a vectorized execution model, right, where I don't have that size of the data I'm at to join as it's coming in. If I'm doing the materialization query processing model, then that's easy because I run the scan, it produces the entire result, then I know the tuples I'm going to access, and therefore I can choose my hash table size. Right? But only MonadDB does that. Most systems don't. So I got to know how big my hash table should be, because I don't want to run out of space and then have to stop everything, double the size, and load everything back in. Right? That makes things super slow. And I can't really do this at runtime because, again, if I'm kind of processing one tuple at a time or a vector at a time, I'm not going to know what the full data is going to look like. And so as I'm doing my query optimization, I have estimates of what the selectivity of predicates are, because that's part of the cost model. So at the same time, I'm picking what join operator I want to use, physical operator. I'm also going to pick how to set things up when I actually run it. So in Postgres, for example, they'll set this value for the hash table size in the query optimizer. You can imagine other things too, like if I'm doing a sort, I may have different sorting algorithms, right? I may have like bubble sort works really great if things are already sorted. So maybe I want to use bubble sort versus quick sort, right? So those are the kind of things you could choose, and they'd be, they would not be distinct physical operators. It'd be a setting or parameter for that physical operator. All right, so we mentioned at the beginning before that outer joins are going to be the tricky one, because just like inner joins, different orderings will make a big difference in the performance of the query. But the challenge is going to be that not all the transformation rules we can apply for inner joins will work for outer joins. Because what will happen is if I start changing the order in which to do joins, then I'll end up getting different matching, given non-matching tuples. Because when I do an outer join, if I don't have a match on say I'm doing a left outer join, for the inner table, if I don't have a match, I'm still going to produce an output tuple. But for the inner table's columns, there's all the values are just null. So depending on the order in which I do a left outer joins, I may get completely different results. So our goal is that we want to be able to either transform a left outer join into an inner join, or do the small transformations that we're allowed to do to still produce the correct results for the non-matching tuples and the null values for the attributes. So the book doesn't really, they sort of explain briefly how to do how to determine whether you can convert things to an inner join, outer join, or outer join to inner join. The basic idea is that if I recognize that I have a predicate on my query that is going to throw away anything that has a null value from the inner side of a left outer join, then it's okay for me to then convert that left outer join into an inner join, because I'm going to still produce the same result here, right? So in this case here, I have this predicate where s.a is greater than 10, right? So that means that if I know that anything coming out of my join is going to ignore anything that where one side is this query actually correct? That should be, b.a, right? Yeah, sorry, R dot A, right? Because this is the left. Say this is the left side. So if I do a left outer join to S, so it means if I join with R, if there's no match in R for S, then R comes out with a bunch of null values, right? Right. So in that case, assuming that it's R dot A greater than 10, well, that means that if R dot A is null, because there's no match between S and R, then I'm checking whether null is greater than 10. Null is equal to nothing, right? It can't, null is not even equal to null. So null greater than 10 is just false. So that means that I'm going to throw away anything that would have been, that is null coming out of this left outer join. So therefore, it's safe for me to convert this into an inner join because it'll be semantically, it's going to be the same result. I'll fix the slides afterwards. So is that clear? Right? And you can do the same thing if it's a right outer join. Full outer joins are more tricky. We can ignore that. Left outer join is just, right outer join is just the inverse of this, right? So again, the reason why we want to do this is because I can't apply a bunch of transformation rules if it's an outer join, but if I can convert it to an inner join, then that opens all the optimizations that we just talked about before. And again, I'm showing it's a two table query here, but if I have dozens of tables, if I can convert a bunch of the outer joins that I have into inner joins, now I can do all the optimizations I want to do to find out the optimal ordering. So this is a big win if we can do this, and you can't always do it, right? Because if I get rid of this where clause, then I can't do that conversion. All right, the last class of operators I want to talk about is group bys. And again, the basic idea here is that if I'm doing a join and there's an aggregation, then it may be the case that I actually want to compute the aggregation before I do the join, because that'll end up reducing the amount of tuples that are being sort of fed into the join operator. Like the joins are always going to be, usually the most expensive thing we're going to compute. And in some cases, I can move the aggregation completely below the join. And in other cases, I can only remove, I still have to keep the one at the root, but I'll basically duplicate the aggregation operator, the group by operator, put that below the join. It's going to compute some partial result that I can then join on. That's going to be much faster than getting raw tuples up. And then on as the output of that join, I'll then compute the full aggregation, the correct aggregation that I would need for the query result. So for a complete group by push down, there's a bunch of rules that you have to satisfy, right? Like the most obvious one, if I'm doing a join and I have an aggregation that only references tuples in one table, then I can easily push that down, right? In other cases, like if I know that the primary key I'm going to look up is a subset of the columns being references, there's a bunch of other rules here, but maybe look at this really simple example, right? I'm going to compute some sum on R.A, but I'm joining R with S on some foreign key reference. So S has a foreign key reference on the primary key of R. But now I'm going to do my group by. It's going to be a combination of the ID and then the RID, which essentially are just the same thing, right? And so in this case here, the initial query plan would look like this. I have my group by and my aggregation being computed above the join, right? But because I know that the only thing being referenced inside of this is are things that I'm getting from S, I can put that below the join. So again, even though I'm referencing R.ID, it's the same thing as R.ID. Sorry, R.ID is the same thing as S.RID. So when I do my join on R.ID and S.RID, then that's going to basically do the same thing as my group by, and then coalesce all the results and produce the correct result. Right? Doing a group by on a column, doing a group by on two columns that has the exact same value, it's equivalent to doing group by on one column. Right? Because if I value ID equals 1 or 2 or 3, if I try to do a group on ID equals 1 and ID equals 1, they're going in the same bucket. There isn't additional subdivision. So in that case here, because I can recognize that these things are equivalent, and then my join's going to be, aggregate or coalesce them correctly in the same order, I put the group by down below the join. And then now again, say this is producing 1 million tuples reading out of S, or billion, always think bigger. But now if I do my group by and there's only 10 unique values coming out of this aggregation here, now my join is based on 10 tuples instead of 1 billion, right? Yes?
If like so that says the primary key of R, can it also be like an unique index as well?
Yes, statement is, I'm saying it's the primary key of R. It could also be a unique index.
Like the uniqueness is the
Unique is the key thing, yes. Let me think about this. So, yeah, so if R is the primary key, but S is a foreign key to S has a foreign key to R, then the S.RD is not guaranteed to be unique. But you know there's going to be a match in R.ID. So I think that's still okay if you just say it's unique. Yeah. Good point. All right, so again, this is a complete group by push down. The aggregate goes completely below the join. But in some cases, you can't always do that. So in this case here, what we can do is we can create a new group by operator that we still keep the original one. We augment it in a slight way. But we're going to make another aggregation. So we're actually going to compute aggregations twice. But in some cases, it actually still may be more efficient because, again, the amount of data that may be coming into the join operator will be substantially less. So in this case here, it's the same query we had before, but now we're doing just group by on this R.B, right? So it's just before we're doing join R and S, group by R.B, and then the aggregation is computed on S.A. So in this case here, we can create a new aggregation that goes below the join, and now we're going to group by on R.ID, which is what our join key is going to be based on, right? Excuse me. Remember I said that this is basically because the join key is the same thing as how I want to coalesce things when I do the group by. So this is matching things up for me. But then now I'm going to compute a partial or sum on these values of R.ID. That's getting fed up into the join operator. And then my group by is being based on the R.B. So as I match the R.ID with the S.RID that's coming up as part of the join, then once I have that match, I know what the R.B value is because I have to do the match. And then that's how I do my additional aggregation. And now I'm just summing all the values that I've generated for each category or each group of RID in this aggregation down below. Snowflake famously does this, right? But they actually do late binding. So they will have a placeholder in the query plan, because it's a distributed system, that the scan starts running. If they recognize that, hey, there's way more data coming out of this than we thought there would, and then this turns on then they would do this partial aggregation pushdown. I think they may always do it, and then I think either they always do it and then they turn it off, or they never do it and then they turn it on. It's one of the two of them. But it's the same basic idea. Okay. So any questions about the group by? All right, I want to finish up talking about the special case scenario. So as I said before, there are some database design patterns that are very common that, if the optimizer recognizes that a query shows up and it's accessing a table, that table is following one of those design patterns, then there are transformations you want to apply immediately, because like, not even worth considering a bunch of different options or join orderings or bushy plans versus left deep chains. Like, there may be things I know this is the right way to do this. Let me go ahead and immediately put you into a form that's going to make my life a lot easier later on, right? we saw a simplified version of this before where we said if a query shows up and it's sargeable, meaning we know it's select star from table where ID equals 4 and ID is the primary key. I don't want to bother maybe even looking at applying all the transformations to the different access methods I have. I know I have an index on the primary key. I'm going to quality predicate on the primary key index, skip all that crap, immediately do the transformation to pick the index that I want for this, because that's nearly almost always going to be the optimal choice, right? So this is the same idea, but now we're looking at a sort of a multi-level query plan that includes joins. So in the book, they specifically talk about how to handle snowflake and star schemas. And again, we mentioned this in intro class, but there's in the 90s there was this very famous book by Ralph Kimball on like data warehousing, and he was basically an early proponent of the star schema. Like you have this giant fact table of like, here's everything, every event that has occurred in my business, like every item someone's ever bought at Amazon or Walmart, whatever. And then you have these dimension tables that are that foreign key references that keep track of like, here's the name of the product, here's the price, here's the location of the store where it was sold at. So then now when I want to do any analytical operations or analytical queries, I'm just joining that fact table with all of the various dimension tables that I have, right? And so the star schema is just, you have one level of dimensions. Snowflake is multiple levels of dimensions, right? So when this shows up, when we recognize that, hey, we're doing a join on the fact table with a bunch of dimension tables, because clearly we have foreign key references from the dimension tables to the fact table, or the fact table to the dimension tables, then I may rather than me exploring all the different bushy plans and different join orderings, then I can just short circuit all of that, have a transformation rule that puts me immediately into a left deep join tree or a right deep join tree. And in some cases, I can also order the dimension tables based on the selectivity of them. It could be something stupid like just the number of tuples that are inside the tables themselves. Or if you actually look at the predicate, you can then determine what the selectivity of doing lookup on them on. So I skip all the bushy tree transformations or anything else, and I say I'm only going to do, in this case here, a right deep tree. Because that's just going to be way faster just to jump to that query plan than doing any possible exploration. And again, if you've taken 721, or I think we talked about this even in intro class, like this is going to be super fast on a column store, right? Because this is like, assume these are all going to be hash joins. So I've got a hash table in dim 3, dim 2, dim 1. And now I'm just going to do a sequential scan through fact table and write that up the pipeline, just probe the hash tables, actually probe the Bloom filter first to see whether it's in the hash table. If it is, then probe the hash table. Like you can just rip through that in my single pipeline, and that's going to be really fast. So what Snowflake does, ClickHouse does, DuckDB, they all do this. So again, rather than dealing with anything else, just go right to the form that I need. All right? And again, when we saw this in Cascades last class, and we talked about Microsoft SQL Server, that they have stages where they apply certain transformations, and this is one of the ones they apply first before they do the cost-based search. If I have a star schema, do this transformation, and that could short circuit things further down the line. Okay? Yes?
How does it determine the schema architecture and the fact that there's a fact table that's really big? Because all it sees really as an optimizer is that, hey, I have 10 tables. One of them is really big. Is that how it just does it? Like, hey, one of them is like 10,000 times bigger than the other one?
Yeah, so his question is, how do you actually detect that it's a star schema? It'll be, you have a single table in your database that only has foreign key references to these other tables, and you don't have multiple foreign keys. It's not that hard, right? Some of you even just name it dimension 1, dimension, like, dimension store, dimension date, like they'll name it that too. Don't rely on that. But like you just look at the schema structure, you'll know, right? In this case here, again, you would know that I have foreign key dependencies between, I qualify this. It's not always going to be blatantly obvious like this. Data is always dirty, schemas get dirty, right? Right, because they might have like fact 1, your table name would be fact 1 and then fact real, right? Like but like in general, you would know from the query, I'm doing a bunch of foreign key lookups from one centralized table to all these dimension tables on the outside. it's going to be, it'll be like that, right?
It can be also like there can be some easy ways to find the patterns, right? Like we know that like suddenly some table has really big references than others, so it's like that can give an idea that it's a star schema.
Yeah, like I said, yes. As you said, like again, it would be the combination of the schema itself plus what the query is doing on the schema. And the point I'm trying to, so I should maybe just say this too. As I said, like it's not always gonna be extremely obvious like this example is. So you apply the transformation that put you into this form, and then maybe there may be additional refinements to change this, right? Or maybe it's something weird where you have two fact tables and you're trying to join them together, right? Like you'll still maybe want to do the additional transformations, but because I've sort of guided the search to get me to this form right away, rather than sort of natively discovering it through transformation rules, then I can start doing the branch and bound, start throwing things away that I know that aren't going to do as well as this. So you still want to do the cost-based search, right? It's just you're sort of pre-populating the memory. It's almost like pre-populating the memory table. It's not exactly the same because there's nothing in it yet, but like you're just saying here's something that's really pretty good at the very beginning, and that's going to allow you to prune out a bunch of stuff later on.
It'll just be like a earlier phase before you get into like cascade.
Yes, but it's different. The populated memory table is like, I guess you could do that too this way. Like you've nudged into a form rather than being a random starting point, like based on the rather than being the initial join order, be based on the order that the table is going to appear in the query, right? I'm putting this form that I know is probably going to be good for me.
Binder will recognize it.
The binder could do it, yes.
Because the rule.
Well, no, yeah. I think about it. That's an engineering point. So the binder could do it, but you don't want to do that in the binder because think about it. That's a query optimization logic.
But it forces you to have rules like these that consider the schema, and most rules don't consider the schema.
They could. They can.
Okay.
But I'm trying to think. The logic of that, like, this is an optimization to do this. Right. This is an optimization to making your search, the search algorithm of your query optimizer better. Don't put that in some other component like the binder. Right? Put that where with all the other logic you have to do query optimization. So yes, the binder could do it, but don't. Yes.
It is understandable that like Databricks and Snowflake use this kind of strategy, but Microsoft SQL Server also does this. But usually people use that as a traditional RDBMS, and probably they won't like adopt column-based. They usually use that traditional speed pass tree. Why would this be so attractive to them rather than to those data warehouses?
Okay, so his statement is that Databricks, Snowflake, pick your favorite, data warehouse system. They're all going to do this. That makes sense. Why would SQL Server do this? Because by default, it's a row store. So why do they care about analytical operations? We will cover this later in the semester. So they have their version of Databricks or BigQuery. It's like Synapse, whatever. So they have, I think I mentioned this before, they took their Cascades optimizer that they built for sort of the row store SQL Server, and they forked it, and they've written it for like, there was a SQL Server parallel data warehouse, and now it's SQL Server, I think it's Synapse. Like they keep changing it. Now it's Fabric, whatever. Keep changing the name. Like, but they had a bunch of different versions of Cascades where they had all these like specific rules in them for their for whatever the system they were trying to target. There's other internal systems at Microsoft too that were based on their Cascades optimizer. Since then, and the last paper we'll read in the semester will be their attempt to unify all that and now have a single code base. So again, to your point, yes, it may be the case that like if you're running the row store version of SQL Server, you don't want to check for this, right? And so to his point, like maybe there's some additional analysis that is being done when you call create table to say, hey, well, this looks like an OLTP schema. Don't enable later on this transformation check in the optimizer.
Can we say that it's kind of like a hybrid, like it's OLTP overlap mix kind of stuff, or is it like
this or SQL Server? Oh,
Sorry, SQL Server is not.
I know, but it's like what, I don't know what category. to put
There's a
it
lot
in.
of like, so this is like the branding thing. Like if you download SQL Server, you're going to get a row store. You can get column store indexes inside that, but at its heart, it's going to be a row store, right? Then there's like the online, again, I think it's called Synapse now, which is I don't want to say hacked up, but they've taken a lot of SQL Server parts and then refactored it to be run in like a data lake warehouse, kind of like Snowflake. Then there's the parallel data warehouse that was built by Jignesh's advisor when he left Wisconsin and went to Microsoft. That was like a shared nothing system. But again, that was also based on SQL Server. So SQL Server is, when I say SQL Server, I think like the thing you download, you run locally, or even their hosted version, it's going to be a row store. But then there's other things that maybe fall under the SQL Server division that maybe still use bits and pieces of SQL Server, like the Cascades Query Optimizer. But maybe the core engine, it may be different. Okay, let's finish up. All right, so the thing to stress is like, okay, we went through some basic optimizations that are kind of obvious, but the generating all of these possible transformations you can have, or any possible query plan you could ever see, that's just almost done through trial and error. Like just go search, pick whatever data sets you want, put bad query plan at the end of it. You'll find all these blog articles that talk about how like, here's the query plan, here's my query, and look how SQL Server, Oracle, Postgres, MySQL, doesn't matter who it is, how they picked the crappy query plan, and like that should have been so obvious, right? And that's, it's a combination because maybe the cost model was insufficient, but also sometimes it's also the transformations just weren't there. It sucks that they archived, Broadcom bought Pivotal or VMware, and they archived the Orca repository on GitHub, and I think they've removed all their issues and pull requests, because in that you would see, hey, here's this query we saw, and we missed this transformation. Oh, here's a new transformation rule that can then catch it for us, right? And this is done through, again, like somebody runs a query, hey, this sucks, why didn't you do this? And then they add a rule to go and do this. Right, so this takes years, if not decades. So what would be really nice is, instead of just, the book covers some basic ones, if there's a way to then extract what's in Cockroach, Calcite, if there's something, is it Mirror or something that was in Orca, maybe just looking at old commits, like it'd be nice to say, hey, here's this library, there's this repository, not targeting any specific one system, although it might be kind of hard to make it more generic, but like, here's all the bunch of transformations you can have. So anyone building a new query optimizer like us could then just bootstrap all these things rather than taking a decade of people running queries and finding mistakes. Like I know, like, again, we'll talk about the Germans next class, like Thomas sits, he has on his phone, he has Slack or whatever the German version of the free version of it, he runs that. And I know he gets notification when someone runs a query in his database system that the optimizer chokes on, he gets an alert and immediately goes and tries to figure out what transformation rule he needs to add to fix it, right? So again, it's just through trial and error, seeing random queries. The fuzzers can't find everything, right? So it'd be nice to have this ahead of time. So the other key thing, we didn't talk about this class, and I said don't read it, and hopefully you didn't. There's a whole part of that chapter about subquery decorrelation. That's super hard. We're gonna spend one entire lecture on how to do this. The book doesn't actually cover everything, actually how to solve it, right? Because there is work that I can't share, at least not yet, where Microsoft has another paper in the works that actually fixes a bunch of things that they can't handle in the book. And then we will read about the German approach. They have a new paper that just came out this month or next month that we have, it's on the website now, that fixes a bunch of stuff that he didn't know about in 2015. So this is super hard. We'll spend a whole lecture on this. The book is incomplete, but we'll cover this in a few weeks, okay? All right, so next class will be your first of many encounters in the semester with the German papers. They're phenomenal. They're freaks in nature. And so we'll think about how they're going to do joint enumeration. So we're switching back to now do bottoms up. So we'll do bottoms up joint enumeration, then top down joint enumeration, bottom up parallelization, top down parallelization, and then unnesting and a bunch of other things. So again, we're now going to go in more detail of, since we have the conceptual framework of what a query optimizer looks like, we're now talking about how we implement those individual components. Okay? All right, guys. See you on Wednesday.
We're gonna go to Brownie. Matter of fact, hold the phone. This is like that wood grain type of shit. Shout out to Blockhouse. My dogs, catch one, nigga out, Mike Stroke, Gumby, or Dynamite. I'm not the one who be amping up the weak ass rhymes. If you spit, if it don't rip through your mind with a sweet anticipated, orchestrated punchline like a reverse the hands of time. Get you captivated quick with the bullshit. I keep the Cadillac equipped for the long trip. I got the remedy for bitches when they start shit. Surround sound like I make them hoes fuck quick and suck dick. Crown me as the thug from the gun. Shit, some niggas claiming never rapping is something. Don't push my button, yes you motherfuckers in front and you don't want